Okay, good morning, everybody. So we finished off the array-based stack implementation at the end of last lecture. And we now want to try to implement
Good morning, everybody. Okay, so today's topic is using collections as fields.
Well,
now this is still
it's video
aggregation and
playing.
composition.
That's funny.
It's just that it's aggregation and composition
Where is that?
the objects that the whole...
Sorry about that. That was the last lecture. Where are we? Where the heck are we? All right, so as I was saying, we finished implementing a stack using an array. We've seen the implementation using a list. We want to implement it now using a linked structure of some kind. Now, because we've got a bunch of different implementations for a stack, it's useful to create an interface and have all of our classes implement that interface. And that way, people who are using our classes can use the different types of stacks interchangeably. So to define our interface, we create an interface called stack. Right? One of our methods returns the size of the stack. I'm going to come back to this method in a minute, but the isEmpty method just returns true. If the stack is empty, it returns false otherwise. Now remember, this is an interface. So normally in an interface, you don't see any method bodies. So this is a bit unusual. Right? Now the other two operations that every stack can perform is push and pop. Right? And so this is for a stack of strings. And we'll also address how to make a stack of anything in a later lecture. Right? So that's our interface, right? It's got 4 methods in it. So pretty straightforward. The default method, though, is new. So we have a default method here. So in an interface, a default method is a method that has an implementation. Any class that implements the stack interface gets the default method for free. Right? In other words, it inherits that method. And so it doesn't have to implement it. The class does not have to implement the default method itself. Right? It has to implement size because size has no implementation. Right? It has to implement push and pop because they have no implementation. But because isEmpty has an implementation, it doesn't need to be implemented. Now, there are restrictions on what you can do in a default method. Right? So notice that the stack interface, it doesn't say how the stack is implemented. Right? There's no fields here. Right? And so the interface doesn't know what's inside any particular stack object. Right? And that means you can't use any fields in the default method. You can't use any non-static fields in a default method, which means you really can't do much with it. So the only thing you can really do is use the methods of the interface. Right? So to implement isEmpty, right, I can use any method that's in the stack interface. isEmpty, to implement it, straightforward, right? You just check if the size of the stack is 0, right? If the size of the stack is 0, then the stack's empty, right? And I can implement it this way because the interface says there's a size method, right? In other words, every stack has to provide a size method, right? So if you decide to implement a default, if you decide to put a default method into your interface, then that method has to be implemented in terms of the methods of the interface itself. Right? Now, default methods, these things only exist inside an interface. Right? So they don't exist for classes. Right? Classes don't have default methods. So don't make a class and then try to mark the method as default. Right? The compiler will flag that as an error. If you decide to put in a default method, the method can only use methods from the interface itself. Right? Or it can also use methods from java.lang.object. Right? So in other words, you can use equals, toString, and hash code for our purposes in a default method. Right? Now, why is that the case? Right? Because you need a class to implement the interface. Right? Every class inherits from java.lang.object. Right? So every class has the methods in object anyway. And so the compiler is smart enough to realize that, and it lets you use any method from the object class inside the interface. So if there was some reason that you needed equals or toString or hash code, you could write your default method in terms of those methods. Right? In other words, you're allowed to use equals, hash code, toString. Right? Now you're also allowed to use any method in what's called a super interface. And so it turns out that interfaces in Java are allowed to inherit from other interfaces. Now that doesn't really, probably doesn't make a lot of sense to you at this point in time, because we haven't quite yet talked about inheritance. And so this will be made clearer, I hope, by the end of this week. Okay, now why do these default methods exist? So they didn't exist in early versions of the language. And so in Java 8, added a big feature to the language, right here. Right, so Java 8 added these things called lambda expressions. We're not going to talk about them. I don't think you guys take a programming paradigms course or have the option to take that course. If you did, you would encounter a different style of programming called functional programming, which looks a lot different than the type of programming you've been doing so far. Lambda expressions are Java's way of bringing in functional programming like tools into the Java language. Right, so we're not really concerned about them. But it's useful to know that these were introduced into the language. Right? Now the problem is when they just introduced this feature to the language, the designers of the language realized that they had to change pretty much every interface that was in the standard library. Not everyone, but most of a lot of the interfaces in the standard library had to change. And that's the big problem with interfaces. Right? So if you make an interface and you hand it out to the rest of the world for people to use, right, people will start to use your interface and implement classes based on your interface. Right? At that point, you have a problem because you can no longer change your interface. Right? If you add a new method to your interface, everybody else's code breaks because their classes, which implement your interface, don't have the new methods. Similarly, if you try to remove a method from an interface, everybody's classes break because their classes already implement the methods in your interface that you want to remove. So implementing widely used interfaces is not a small deal, right? If your interface becomes widely used, then it becomes impractical to add new methods or to remove methods from an interface. And that's the problem that the designers of the language had, right? They added a new feature, had to change the interfaces, didn't want to break everybody's code, right? So what did they have to do? They decided that to introduce these new features, they needed new methods in a lot of their interfaces, right? They can't put the methods in the interfaces without causing everybody else's code to break, right? So what they did is they introduced default methods into the language, right? So they put default methods into interfaces. Those methods have implementations. So everybody else's code that implements those interfaces, they now get those interfaces for free, those methods for free. Right? And so that's why these exist in the Java language. All right, so that was a little bit of a detour. Let's go on with making, so let's modify our array list-based stack so that it now implements our stack interface. Right, so we've got two existing stack classes. Right? One of them is an array list-based stack. Right? We also have an array-based stack, but our array-based stack is a stack of int. Right? It's not a stack of string. And this interface right now is for a stack of strings. Right? So I can change my the array list-based stack to implement this interface. I can't yet change the array-based stack, but we'll come back to that later. Right? So it's easy to have a class implement the stack interface. Right? Just change the name of the class, because our old class name was stack. So now I'm going to call it list stack to indicate that this is a stack that uses a list, right? And then you write implement stack, and you're done. You don't have to do anything else, right? Because our list stack already has size, push, and pop. Right? So we don't have to. The change for our class to implement the interface is very small, which is nice, right? And that fixes that problem. Right? Now, what about implementing our third kind of stack? Right, so here we want to implement a stack using these things called nodes. Right, so, and the reason we want to do this is because there are two existing stacks. Their pop operation always has worst case complexity big O1. Right, so pop removes an element from the end of an array or list. Right, that always takes constant time. The problem with push that we've seen is that every once in a while you have to expand the size of the array, or you have to expand the size of the storage that the array list is using. right? Every time you expand the storage of an array or an array-based list, right? That has worst case complexity big O n. Right? So every once in a while, push occurs in big O n. Most of the time, it's big O 1, but every once in a while, it's big O n. Right? And there are some circumstances where you need a stack, a high-performance stack, and you cannot pay the price, or you're not willing to pay the price of a big O n operation. Right? In other words, you always want big O 1. The only way that you can guarantee that is you either fix the size of the stack and say that you can't expand the size of the stack, or you have to change the implementation of the stack. Right? You have to change the way that you're storing the elements. So we're going to do the second. We're going to change the way that we store the elements. Right? And so what we're going to do is we're going to use these things called nodes. Right? And many data structures use this type of representation. So many data structures are basically collections of some kind of nodes. Right, so in this course, we're going to do linked lists and linked queues, possibly, using nodes. Trees, if you see them, which you probably have seen in your previous data structures course, those are all node-based, usually, not always, but usually. Graphs, which you might have seen in your data structures course, but I suspect not, are often implemented as nodes or using nodes. If you take the algorithms equivalent of 365, you'll see graphs. Right? In which case, you're going to see nodes. If you end up in the math course, which is a graph theory-based course, so it's actually the mathematical theory of graphs, you'll also see nodes. So what's in a node? A node stores an element, right? Or a reference to an element in Java, right? And then it also stores a reference to 0 or more other nodes, right? And so those references are called links. Right? Now, it's not a collection of other nodes. Well, sorry, that's not true. It's a reference to 0 or more nodes. So let's look at a picture of that. Okay, so here's a picture of what a node's going to look like in our stack. Right? So a node holds an element. Right? So there's our node holding. This is a node for our stack class, where each node holds a string. Right? And each node holds a reference or a link to the next node in the stack. Right? Now, if you only have one node on the stack, right, then this reference here is null, right? It points to nothing because there is no other element on the stack. So if I push another element onto this stack, what do you need to do? Right? Well, number one, I need to make a new node. Right? So I make a new node, and I store the element that I want to push onto the stack in that node. Right? So here I push the B onto the stack. Right? And then I make that node, right? I make its link point to the next node. Right? So you add a link pointing to the next node. Right? And now if you're at node B, if you follow the link, right, you can get to the next node A. Right? Now you adjust the top of the stack so it points at B. Like that. Right? And then finally, if you're keeping track of the number of nodes in the stack, you add 1 to the size of the stack. Right? This step here is optional. We're going to keep track of the size of the stack ourselves. It turns out there's a way to compute the size of a stack if you need to. Right? Okay, so let me back up a slide now. Okay, so what's so for our stack class then, our stack is just a linear collection of elements, right? So there's the top element, then the next element, then the next element, and so on. Right? So elements are arranged in a sequence, starting from the top element, right? And each element is connected to the next element deeper in the stack. Right? And so for our node, we're going to store the element, and we're going to store that reference to the next element deeper in the stack. Right? So that's what our node structure looks like. Now, if you draw a UML diagram of the node structure, of the node class, it's going to, oops, sorry, popping. Where's the UML, hang on. Oh, there it is, okay. All right, so if I want to pop an element off the top of the stack, right, so I want to remove the C from the stack, I have to return the C. Right, so I'm going to remember what value is at the top of the stack. So I'm going to obtain a reference to the element stored at the current top node. Right, so I remember that there's a C there. Right, I then want to remove that node from the stack. Right? So the way to do that is you just move top so that it points at the next node. right? So I'm just going to move top so it points to the B. Now the way you do that is, right, so top points at the C right now. So to get it to point to the B, you just follow the link from the C to the B, right? And now that lets you point to B. And that effectively removes the element at the top of the stack, right? Because you no longer have a reference to that element. So in Java, the garbage collector will eventually come along and get rid of that node for you. Okay, I'm going to subtract 1 from the size of the stack because I've removed the element from the top of the stack. Right? And then I'm going to return that reference to the element that was stored in the previous node. Right? So in other words, I'm going to return the A back to the caller. Okay, so if you draw the UML diagram for a node, it looks as follows. Right? So a node is made up of an element. Right? So in other words, a node, right, is going to be an aggregation of one string. Right? So I'm using aggregation here instead of composition because every collection in Java, in the Java standard library, uses aggregation for its elements, right? So a collection stores references to its elements, right? It doesn't store or doesn't own the elements themselves, right? So we're going to use aggregation here, right? We also have this other, the link, right? So the link we're calling next. Right, so a node points to the next node in the sequence. So every node has a link called next that refers to another node. Right? Now, a node is not made up of another node. Right? So in other words, a node doesn't try to own another node. Right? So this here is association and not aggregation. Right? So node has a next node, right? And node what is made up of a string. All right, so here's what our linked stack class is going to look like. So we've got a class called linked stack, right? It's going to implement our stack interface, right? So in other words, we're going to make a stack of strings. We're going to keep track of the number of elements on the stack, right? And we're going to keep track of where is the top of the stack. So what node, right, is at the top of the stack. Right, so our type here is node. Right, now where's our node class? So our node class is inside of our linked stack class. Right, so inside linked stack, we've got a class called node, and it's private. Right, so in other words, we're trying to hide the fact that that the linked stack is made up of a sequence of nodes. Right, we don't want anybody else to access this class. Which means it's only accessible inside the linked stack class itself. Right? It's also static, so I'll explain that in a second. Right? Now, what's a node made up? What is a node made up of? Right? Well, it's made up of string. Right? So it has an element that we're going to store in the node, and it has a link to the next node in the sequence. Right? So that thing there next, if it's null, then there is no next node in the sequence. Right? So in other words, you know you've hit the bottom of the stack. Right? If it points to some other node, then you know that there are still more nodes in the sequence. Right? And we've got a little constructor here that simply sets elem and next. Right? Notice there's no copying happening here, right? Because we're not using composition. Right? So it's just straight up association and aggregation. Right? So this elem is not equal to new string elem, right? And this next is not equal to new node next. Right? It's just equals elem equals next. Right? So there's our inner class. Sorry, this is a nested class. Okay, so this class is inside of another class, which means it's a nested class in Java, and it's also marked static. So this is called a static member class or a static nested class. And this turns out to be the simplest kind of nested class in Java. Right? So the previous nested class that we saw was called an inner class. Right? And that's different than a static class, a static nested class. Right? Okay, so what's a static nested class? So it's just a regular class that happens to be defined inside of another class. Right? So that's all it is. Right? Now, unlike other kinds of nested classes, right? So unlike the inner class we talked about previously, right? A static member class cannot access the private members of the enclosing class. Right? So node cannot access size or top from the stack class. right? Node can only access its own fields. Right? So in other words, a node does not have access to the private fields of linked stack. Furthermore, you can have a node without having a stack, right? Because this is just a regular, it's just an ordinary class that happens to be defined inside of another class. Right? So in other words, a node can exist without having a linked stack class. Right? Furthermore, a node does not have a reference back to its enclosing class. Right? Whereas in an inner class, right, the inner class does have a reference back to its enclosing class. So a node object can exist without belonging to a linked stack object, right? Because it's just a regular class. Now the reason, so you should if you can, right? So if you decide that you need a nested class, then you always have to decide, am I using a static nested class or am I using an inner class? Right? If you can, you should use a static nested class because they use less memory than an inner class. Right? There's no reference to the linked stack object. Right? Whereas with an inner class, there's always a reference back. Every inner class object has a reference back to the outer class object. So, static member classes use up less memory than inner classes. All right, so now to our constructor. So that's it for our static, that's all our class looks like. So that's all it is, right? It's just two fields and a little constructor. Okay, so what does our constructor for the stack look like? Right? Well, it sets the size of the stack to 0, right? And it sets the top node to null, right? So there is no top node, right? Which makes sense for an empty stack, right? We have to implement the size method because we're implementing the stack interface, right? So how do you get the size of the stack? Well, I've got this field called size, so I'm probably just going to return this dot size. Right? Pushing an element onto the stack, so just remember what it looks like, right? So if I want to push an element onto the stack, right, I make a new node, right? So in our push method, we're going to make a new node, right? That's the first thing we're going to do, right? We're going to set the link of that node to point to the current top element of the stack, right? Then we're going to adjust the top element of the stack, right? And then we're going to add 1 to the stack size, right? So we're just going to do these 4 things, right? And we're going to do steps 1 and 2 all in one shot because we've got a constructor that does it for us. Right, so make a new node, right? New node, right? We're going to store the pushed element in the node, right? So we just call the constructor with elem, right? We want to point the new node's next link so that it points at the current top of the stack, right? So you pass in this dot top for the next link, right? So the constructor sets the next link of the node to point to the current top node, right? And that's what that constructor does. Or that's the side effect of that constructor, right? Now we have to adjust the top node so that it points to the new node, right? That's easy. This top's just equal to n, right? And then step 4, increase the size of the stack by 1, right? So pushing a node onto the top of the stack is trivial, right? Well, it's almost trivial, right? You just literally follow the steps on the slide, right? Now what about popping? Anybody have any questions about this method? Right. You have to keep in mind that in Java, these nodes, right, every node's a reference. Right? So in other words, if you're still in the mode of trying to translate C into Java or Java back to C, right, you should just think of a node. Every time you write node n, that's just a pointer. Right? So that's a pointer to a node of some kind. Right. Okay, to pop an element off the stack, I need to remember what's sitting at the top of the stack. Right? So I need to remember that there's a C sitting at the top of the stack. Right, so I'm going to get a reference to that string. Right, I'm going to move the top node so that it points at B. Right, and the way I'm going to do that is I'm just going to follow the current top's node next link. Right, so if I follow that next link, that gets me to the next node. Right, so I can easily adjust the top of the stack. Right, removing the element I don't have to do. The garbage collector is going to do that for me. Right, so it'll get rid of freeing the memory associated with the node, and I just subtract 1 from the size of the stack. Right, and that's it. Oh, and then you return the element that was in the top of the stack. Right, so that's also easy. Right, so to pop a stack, ignore the if statement for now. Right, so step 1, right, get a reference to the element that's currently at the top of the stack. Right, how do I get that reference? Well, I just go into the node, right, access the element. Now, linked stack is able to access the private fields of a node, right? Because the node class is defined inside of the linked stack class, right? So as far as Java is concerned, the node class is just like a regular field, or it's treated as though it were a member of the linked stack class, right? Which means that linked stack can access all the private stuff inside of a node. So you can just write this.top.elem, right? You don't have to call a public accessor method to get the element. Right. Now, how do I adjust the top reference to point to the next element in the stack, right? All I write is this top equals this top dot next. Right? So remember that this thing next is just a pointer to the next node, right? This top is just a pointer to a node, right? So if I want to move, or I want to adjust this pointer to point to the next element, right, I just write this top dot next. Right? Decrease the size of the stack, return the element that was previously at the top of the stack, right, which I remembered back here. Right? I guess, so if you try to pop an empty stack, right, you should throw an exception. Right? So I'm just going to check if this is empty, right, throw a runtime exception. You're trying to pop an empty stack, right, and that's pop. And that's it for the stack class, right? So that's all that you need to implement in the stack class, right? So we implemented the 3 methods that we had to in the stack interface. Right, now, to make this class usable for people, you probably want to provide a toString method, right? And an equals and hash code if you're implementing equals, right? So for toString, I need to generate a string that you probably want to generate a string that contains the string representation of the elements in the nodes. Right, so if I have the stack A, B, C, if I have the stack A, then B, then C, you probably want to generate the string C, then B, then A for the stack representation, right? So from top down. But here I've got a problem, or a small problem anyway. Right? If you go back to the stack implementation, right, there's nothing inside of a stack. Right? All you've got is the size, and all you've got is a pointer to the top element, or to the top node. Right? You don't actually have a way, there's no collection sitting in here. Right? So there's no list, there's no array sitting in here. Right? You don't have a list of nodes, you don't have array or a list of nodes. Right? And so in order to generate the string sequence, you have to manually follow that sequence of nodes yourself. Right? So to implement toString, I need to iterate over the sequence of nodes. Right? And in a lot of these types of linked structures, right, one of the fundamental operations is iterating over the sequence of nodes. Right? In a tree, you've got a different problem because you have to go to both sides of in a binary tree, sorry. You've got to go to both branches of each node, right? A graph, there can be an arbitrary number of nodes. There can be an arbitrary number of next links for every node. So now you've got the problem of I have to go to every next link for that node, right? But for a singly linked structure, it's pretty straightforward. You just follow this with the one next node, then the one next link every time, right? How do you know when to stop, right? So you know that to stop, the bottom node of the stack, its next link is null. Right? So all you have to do is follow the sequence of nodes until you hit a null link, right? Which is pretty easy, right? So I start at the first node of the sequence, right? You simply follow each next link to the next node until you hit a next link that happens to be null. Right? When you've hit the null next link, you know that you're done. So it's straightforward to iterate over a sequence of nodes. Right? So you start out, right, with a node n, right? And you just set that to refer to whatever starting node you want. Right? So normally we're going to start at the top of the stack, but you might want to start somewhere else. You might want to start somewhere in the middle for some reason. Right? So n is going to point to the current node. Right? So it starts by pointing at the starting node. Right? As long as n's not null, you can do something with n. Right? If n is null and you try to do something with n, then you get a null pointer exception. Right? So never try to do something with a null node. Right? So check, is n not null? If n's not null, go ahead and do something with n. Right? Either get its element or do something, right? And then you advance n. So now you take n, right, and point it at the next node in the sequence. Right? When you hit the bottom of the stack, right, so when n's currently pointing at the bottom of the stack, n next is null. Right? So when you come back up to the top of the loop, n becomes null, and the loop doesn't run. Right? Now, when you get down to here, right, whatever you do, don't use n after the loop, right? Because n's going to be null if you end up past the loop. Right? Now, there are times when you do need to use a reference to whatever. So there's times when you want to iterate over a sequence of nodes, and you want to keep that last reference, right? So in other words, I want that bottom node for some reason, right? So if that's the case, you have to, there's a couple of ways you can deal with this. You can create a second node variable, right? So node m, right? You start that equal to null, right? And then here, before you update n, you write m equals n, right? So that remembers what the current node is, right? Before advancing the current node. Right? And then when you end the loop, m is equal to the bottom element of the stack, or points at the bottom node. Right? And you can actually generalize that. So if you want to remember what the second from the bottom is, you just make a third variable up here, right? And update it to m every time in the loop. Okay, so to generate the string, what does the picture look like? So the picture of this loop ends up looking as follows, right? So n is going to start by pointing at the top of the stack, right? While n's not null, while n, back up, right? So n points here, right? N next now is that thing there, right? So that's part of the thing, that's one thing that you have to wrap your head around, right? So n points at that node, right? N dot next is that node's next link, right? So it's whatever this node points at, right? So while n's not null, right? So n points at a node, it's not null, right? N equals n dot next, which is the same thing as saying n equals this node dot next, right? So it now points at the b, right? Is n null? No, it points at a node, so n equals n dot next, right? N next is that node's next link, right? So we move to the bottom node, right? Is n null? The answer is no, right? So n equals n dot next, right? So that's that node's link. So in other words, n equals null, right? And you're done. Okay, so to generate the string representation of a node, right? I guess I'm going to use a string builder to do this. String builder is just the mutable version of string, right? So if you need a mutable string, use string builder, right? Which in other words, the string builder object b is pretty much like a string, except I can add stuff or I can change characters in the string builder object, and so on and so forth. So I'm going to start out by making the string be just stack, right? So I'm actually going to print out the word stack, right? I'm going to start by pointing at the top node, right? And then I'm just going to use my general iteration pattern, right? Well, n's not null, I'm going to append a new line to the end of this string, right? Then I'm going to append the string representation of the element, right? You can also write n.elem.toString, right? If you don't write the toString, the compiler will stick it in for you, right? So it's n.elem, right? So that appends the new line followed by the element, right? And then you advance n to point at the next node, right? When you're done, you just return b toString. Right? So here you have to explicitly call toString because toString needs to return a string object. Right? So I need to call b's toString method to actually get a string object. Right? And that returns the string representation of your stack. Right? So that ends up printing something like, so if you have a stack ABC, you end up getting stack colon, then you get the the C, the B, then the A. Right? So it prints out the stack from the top down. Okay. Anytime you implement something using a node, right? So in other words, you've got a node that points at one or more, or zero or more other nodes, right? then that node class is an example of recursion of structure. Right? So what do I mean by that? Right? So what I mean by that is that every node has a reference to another node. Right? That node has a reference to another node. Right? That node has a reference to another node, and so on and so on and so on, until you reach the bottom node. Right? Because the bottom node, that's when its reference is null. Right? And so that structure of a node is recursive. Right? So what does that mean? Right? That means you can view every node as being the top node of some stack. Right? It's not the top node of the original stack, right? But every node is the top node of some stack. Right? Do I have a picture here? No. Where's the, okay, here. So, for example, C is the top node of this stack. Right? B is the top node of the stack of size 2. Right? A is the top node of a stack of size 1. Right? Because the structure of a node is recursive, right? That makes it very easy to write recursive algorithms using that operate on the node class. Right? So for toString, I can change the loop, the iterative version of toString, I can change it into a recursive version of toString. Right? And it's pretty easy to do. Right? So this is a second implementation of toString that's going to use recursion. Right? So we're going to start out, again, by making a string builder object, right? And having the string builder object be the string stack. Right? I'm going to start at the top node of the stack. Right? And then I'm going to call this method called toString helper. So toString helper, this is our recursive method. Right? It's got the name helper because it's a helper method. So it's a method that this is the method that actually does all the work of toString. Right? And it turns out it's recursive. Right? So it has as input a node n. Right? So that's how this thing's going to work. Right? So we're just going to recursively pass in some node n. The method has to be private here because one of its parameters is a node. Right? And the node class is only accessible. The node class is private inside of the linked stack class. Right? So if I make this public, there's no way for anybody to use this method because it takes in a node and they don't have access to nodes. Right? So the method's private. Right? toString helper recursively returns the string representation of a stack. Right? So how does this work? Right? So if n is null, right, then what do you know? You know you've reached the bottom of the stack. Right? So in other words, you know that the string representation of the stack of size 0 is the empty string. Right? That's what that's saying. Right? So if you have an empty stack, then the string representation of the empty stack is the empty string. Right? It's actually stack followed by the empty string. Right? Because we're going to append the return value of the toString helper method to that string there. Right? So if you reach the bottom of the stack, you're done. Right? You just return the empty string. If you're somewhere in the middle of the stack, right, what do you want to do? Well, I want to append the new line to go to the next line. Right? So I start out with stack. I want to append a new line so that I go to the next line. Right? So append the new line. Right? Then append the next element. So I want to append the C. Right? And then I want the string representation of the rest of the stack. So that's what toString helper n.next does. Right? It generates the toString representation of the remaining elements in the stack. Right? So toString helper, right? If you were to look at if you were to look at the documentation for this method, it would say it generates the string representation of the stack whose top node is n. Right? So if I print out one element of the stack, or I generate the string representation for the top element of the stack, right? Then the string representation of the rest of the stack is just whatever the rest of the stack is. Right? You know that every node can be thought of as the top of the stack, of a stack, right? So you want the string representation of the rest of the stack. Right? So that's just the stack starting at the next node. Right? So that will recursively compute the string representation of the stack, right? And then you return S at the end, right? And that produces, that's the recursive version of a toString. All right, any questions about that recursive method? Right, so this turns out to be very common in these node-based structures, right? You can easily convert the iterative version of the method, right, to its recursive version, right? The way you do it is you introduce a private helper method, right? The private helper method usually takes in a node. It might take in other information depending on what your problem you're trying to solve, right? But normally it takes in a node. Every recursive method has to solve a smaller version of the problem, right? So typically inside the helper method, it recursively calls itself by passing in the next node, right? And that guarantees that it'll eventually reach the case where n is null, right? Assuming you don't run out of memory while you're doing the recursion. So there's an example of using recursion on a linked structure. All right, any questions about linked-based node stacks? Anybody? All right, I think that's going to be it for today. I don't know what we're doing in the next class. I'll have to, I don't remember what the next lecture is, but I guess we'll see. So see you in 2 days. Your next assignment comes out probably today or